Section 10.1 is parametric functions. So we're going to start by doing a review of changing parametrics using algebra or trig to write an equation relating x and y. So let's look at number 1. We have x equals t plus 1, y equals 2t plus 3. When we have algebraic equations, we're going to just simply use a substitution. I'm going to solve this equation for t equals x minus 1, and I'm going to take and substitute that. Let me try and get rid of that squiggle that appeared. I'm going to try and substitute that into this equation, where I will get y equals 2 times x minus 1 plus 3, which gives me y equals 2x plus 1. So that's my xy equation that matches these parametrics. Try number 2 on your own. Okay, so again, if x equals 3t, I can solve for t. Substituting that into the other equation, I get y equals 54 times x over 3 squared minus 3. That's 54x over 9, which is 6x squared minus 3. Okay, let's try one of the, I'm going to go ahead and just erase this, so write it down if you need it. I'm going to try some of these trig ones. This is the simplest of the trig functions to convert to an xy. We just say x squared plus y squared, adding this plus this squared, is the same as adding sine squared t plus cos squared t, and we know that that equals 1. So this is the equation in xy form of a circle centered at 1. Now let's take a look at number 4. 4 is a little trickier, and we need to use a trig identity. And the trig identity that we're going to use is, instead of saying that y equals sine of 2t, we're going to say that y equals the same as 2 sine t cos t. All of these trig identities can be found on page 565 in your text. So you might want to open up to that. So this is my y. I know that my x for number 4 is sine t cos t, and y is 2 sine t cos t, so I can just say that y equals 2x. So this is a linear equation. It sure doesn't look like it when we start with something like this, but it's a very simple linear equation. Okay, see if you can do number 5 on your own. Pause and come on back. Okay, number 5. Again, I'm going to think about some trig identities. Tan theta, y equals secant theta. So I'm going to again use one of my Pythagoreans. I'm going to start with 1 plus tan squared theta equals secant squared theta. Doing some substitution here. And there's my equation. So y squared equals 1 plus x squared. All right, the last one, number 6, you're also going to need a trig identity from the book. So we're going to use the fact that cos of 2 theta is the same as cos squared theta minus sine squared theta. See what you can do. See if you can figure out how to change this to an xy. It takes a little bit of work. Come on back when you're ready. Okay, give me some room here. And this is the identity we're going to be using. Whoops. So let's see what we've got. I've got x equals sine theta, and I'm going to change y to cos squared theta minus sine squared theta. Alright, so I know that I can substitute x in for this, but the problem is, what am I going to put in for my cos squared? So I'm going to use another identity. Cos squared theta is 1 minus sine squared theta from our Pythagorean. So now I have 1 minus 2 sine squared theta, which is 1 minus 2x squared. Okay, so that's it. We're going to continue to work on these as we go through our parametrics. Oh, there's the answers again. Okay, so let's talk about some parametric curves. We've already touched on one of them. Sketch the parametric curve and eliminate the parameter to find an equation that relates x and y. So this one we did very similar. The x and the y were switched, I think, but this is a parametric. So let's see. In order to graph this, that's the first thing they want me to do, is to sketch the curve. I'm going to set up a t, x, y table. Since I'm going from 0 to 2 pi, I'm going to use 0, pi over 2, pi, 3 pi over 2, and 2 pi. So I'm going to do all my x's first. X is the cosine of t. So when t is 0, x is 1, pi over 2 is 0, negative 1, 0, and back to 1. My y values are my sine values, so 0 is 0, then 1, then 0, then negative 1, then 0. So here is the curve, and again starting at 1, 0, but then I'm going, I'm still going the same direction, 0, 1, so I'm going in this direction, and then I want to find my equation. So this is going to be exactly the same as the one I did before. X squared plus y squared equals cos squared plus sine squared. So x squared plus y squared equals 1. Okay, let's try another one. This time we've got some coefficients, and we're doing the same interval. So again, I'm going to start with a t, x, y. I'm going to use my same values for t. So now my x values are cosine again, and so I'm going to start at 1, but since it's multiplied, I'm going to start at 3, 0, negative 3, 0, and 3. My sine, or my y values, are going to be 0, 2, 0, negative 2, 0. There's our curve as we plot it. So that's an ellipse, again starting at 3, 0, going up to 0, 2, so the ellipse is going in this direction. So how are we going to change this to an xy equation? Well, the first thing I'm going to do is divide by 3 and divide by 2. Now when I square both sides, x squared over 9, adding it to my y squared over 4 equals my cos squared t plus sine squared t. So now I have an equation of an ellipse centered at 0, 0, whose x-axis is 3 units from the center out and y is 2 units. So that works nicely for an ellipse equation. Let's try one more. So this one doesn't have any trig in it. We're still going to set up our table. So 0 to 4, 0, 1, 2, 3, and 4. 0, x is the square root, so square root of all of these. Y is t minus 2, so 0 minus 2, 1 minus 2, 2 minus 2, etc. And if I plot this curve, it will look something like this. So this is part of a parabola, it looks like. Let's see what happens when we change our parametrics. If x equals root t, then t is x squared. If y equals t minus 2, y is x squared minus 2. That is a parabola who is shifted down 2 units. We have to keep in mind that since we're just taking the interval from 0 to 4, this is not going to be the entire parabola. So that's some work with parametrics in general. Now let's talk about differentiation. So if x and y are both differentiable functions of t, and if dx dt does not equal 0, then dy dx is dy dt over dx dt. So remember, each individual derivative needs a implicit differentiation. Another way to write this is dy dt times the reciprocal of the denominator, and we can see by simple cancellation that this would be dy dx. If y prime is dy dx and is also differentiable, then the second derivative, d dx of y prime, is dy prime dt over dx dt. Now again, this can be found, it takes quite a bit of derivation to get there, so right now just trust me on this and we will work with one in a moment. Okay, so let's analyze a parametric curve. We're going to consider the curve defined parametrically by x equals t squared minus 5 and y equals 2 sine t from 0 to pi. So there's 3 things we want to do. We want to sketch a graph of the curve from -7 to 7, -4, 4, and indicate the direction in which it's traced. Then we're going to find the highest point on the curve. Remember, the highest point is when y prime equals 0 and when it has a change in signs from plus to minus. So we're going to be looking for that. And points of inflection, we're going to be looking at y double prime. So let's start with our curve. So again, my formulas were x equals t squared minus 5 and y equals 2 sine t. So again, and I think we were going from 0, let me go back and look, from 0 to pi. So I'm going to just very quickly take a couple of values here. I'm going to just use 0, pi over 2, and pi. Now if we were actually curve sketching this, we would do a few more, but I'm going to keep it simple. When I put these values into t, or into x, I get -5. Pi over 2 squared minus 5 using my calculator is about -2.5, and pi squared minus 5 is about 4.9. My y values are going to be 0, 2, and 0. So if we sketch this, and you see they've given us our direction here, we get a curve that looks something like this. Okay? All right, part B asks us to find, I flipped my page over here. Part B asks us to find the highest point on the curve. So I need to find when dy dx equals 0. Well, dy dx is dy dt over dx dt. So let's first find dy dt. X equals t squared minus 5, y equals 2 sine t. Dx dt is 2t. Dy dt is 2 cos t. So dy dx equals 2 cos t over 2t. I can simplify that to cos t over t. Now in order for this to equal 0, cos t has to equal 0. And the only place where that happens is at t equals pi over 2. Now, plugging that into my calculator, and we did this on the last slide. When t is pi over 2, I get the ordered pair negative 2.5, comma 4.9. The question is this a max or a min? So let's look at pi over 2. To the left of pi over 2, I get positives. To the right, I get negatives. So therefore, this is a maximum. So that's first derivative of a parametric. Okay. C asks us to find the points of inflection, so I need the second derivative. So remember, dy dx was cos t over t. To find my second derivative, I need the derivative of dy dx, so I need dy prime dx over, wait, I'll make sure I'm writing it the right way, over dx dt, right? There we go. So let's find the derivative of cos t over t. That's what needs to go on top. So this is going to require a chain rule. So I'm going to use low times the derivative of high minus high times the derivative of low. I'm using this to do my quotient rule over the square of what's below. So the numerator of my second derivative is the derivative of my dy. So this will be, I'm going to clean it up a little bit, negative t sine t minus cos t over t squared. The denominator is just dx dt. I found from before that dx dt was 2t. So again, cleaning all of this up, that is my second derivative of the parametric. Now I used my calculator, plugged this in to find zeros, and the only zero on my interval was at t equals 2.7983. We'll do a lot of practice on these, so no worries. Alright, the next thing we're going to look at is the arc length of a parameterized curve. We did arc length of a curve before in section 7.4, and we found that the length of the curve was the integral from a to b of the square root of 1 minus dy dx squared dx. And this came from playing around a little bit with Pythagorean and that stuff. So we're going to do the same thing with parametrics now. Let L be the length of a parametric curve that is traversed exactly once as t increases from t sub 1 to t sub 2. In other words, a curve that doesn't double up on itself. If dx dt and dy dt are continuous functions, then the length of the curve from t sub 1 to t sub 2 is the derivative of dy with respect to t squared plus the derivative of x with respect to t squared. So let's try one of these. Measuring a parametric curve. Find the length of the curve. So the first thing I need to do is to find dx dt, which in this case is cos t, and dy dt, which is negative sine t. So the length of the curve from 0 to 2 pi. This, we know from past experience, is a circle. So I could parameterize it all the way from 0 to 2 pi, but if I just find the length from 0 to pi over 2 and multiply it by 4, I'm in good shape. So the length equals 4 times the integral from 0 to pi over 2 of the square root of dx dt squared plus dy dt squared. When I square something, it becomes positive dt. Well, that's really nice because this is the square root of 1, which is 1. So this becomes 1 dt. Taking the antiderivative, 4 times t evaluated from 0 to pi over 2, which is 4 times pi over 2 minus 4 times 0, which will give me 2 pi. So the length of this curve is 2 pi. That should not really be any surprise because the circumference of a circle with radius 1 is, wait a minute, what have I done? Oh, not pi r squared, that's area. No wonder, my brain's gone berserk on me. 2 pi r, that's better. So the circumference is 2 pi when the radius is 1. So kind of just an interesting way to find a circumference using parametrics and the length of a curve. So that's it for the video. We're going to work on this quite a bit, and I will see you in class.